So hello friends, we'll be learning today about relations and functions, chapter 2. So what are all the key points we'll be going into? So what is the first key point? We'll just see. So how to develop a connection between two sets or objects called as Cartesian products. How to establish a relationship between two sets, that's a relation, and which relation is called a function, that's a function. So we'll just see what are these three types. So going into the first topic, that is how to develop a connection between two sets. Just look into this. Now two sets or two objects, if you're taking any two objects, whenever you're taking connection, it means between two things or two objects or two sets we have to compare. In general, I have taken these examples. Now in mathematical terms also you can have connections, isn't it? So what are those connections? We'll just say A is perpendicular to B, we can say. A is parallel to B, we can say. A is greater than B, we can say. A is equal to B, we can say. A is less than B, we can say. So here these are the different types of notations we can take, and we are having some connectivity between A and B. How is A related to B? How is B related to A? Suppose we define a set A as ABC, set B as 1, 2. So now here, what is this A cross B equal to? That is a product of two sets. So how are we writing this product of two sets? We are writing it as A1, B1, C1, A2, B2, C2 with a comma in between. Brackets have been written, and you have closing with the braces. That is nothing but A cross B. So here you are having the first element A is from set A, the second element is always from set B, that is 1. You can see that the first element, even B is from set A, 1 is from set B, again C is from set A, 1 is from set B. So in the same way, A comma 2, B comma 2, C comma 2. Now what is this? This is nothing but Cartesian products. Cartesian products, it is nothing but, it is the product of two sets. We are taking set A and set B. This is nothing but the product of two sets. So what is the definition? We'll see. Given two non-empty sets P cross Q, the Cartesian product P cross Q is the set of all ordered pairs. Whatever written in the curved brackets are all ordered pairs whose first component is a member of P and second component is a member of Q, and it is denoted by P cross Q, where the first component is a member of P and the second component is the member of Q. That is the first set and second set respectively. So now we are taking one example. We'll see what is this example. P is equal to 1, 2, 3. Q is equal to 1, 4, 9. So how do we write? What are all the possible combinations? We'll just see. P cross Q is equal to, we are taking 1 from the set P and 1 from set Q. 1, 4, 1. Here you can see, taking 1 from here, 1 from here, then 1 from here, 4 here, 1 from again first set, then 9 from this. Similarly, we can take 2, 1, 2, 4, 2, 9, then 3, 1, 3, 4, 3, 9. So what is the definition of ordered pair? We'll just see. Ordered pairs. In the ordered pair AB, A is called the first component and B is called the second component. In general, AB is not equal to BA. We cannot write it as 4, 2 or 4, 3 or 4, 1. Always the first and the second should be written. So here A is called the first component and it has to be written first, and B is called the second component, it has to be written second, that is from the second set. So therefore AB is not equal to BA. You can see here it is very clear. See, an important point to be noted down. So two ordered pairs are said to be equal if and only if the corresponding first components are equal alongside the corresponding second components are equal. So here you have AB is equal to CD if and only if A is equal to C and B is equal to D. So order is important over here. You are writing A here, then C over there. If you are writing it as A D C, again it is not equal there. If you are writing AB is equal to DC, it's not equal. Order is important. Therefore, AB is equal to CD, A is equal to C, B is equal to D. Now, what is A cross B? We'll prove that why A cross B is not equal to B cross A. You can see here. Now A is equal to AB and B is equal to 1, 2. A cross B is equal to, now A is the first set and B is the second set. So how do we write that? We write it as A1, A2, B1, B2. You're having totally 4 ordered pairs are in this. So what are those 4 ordered pairs we can see here? Now again, what is B cross A? B cross A, we are taking B as the first set now. So we'll start from 1, then A, 1B, then 2A, then 2B. So we are getting, therefore A cross B is not equal to, you can see over here, A1 is not equal to 1A, A2 is not equal to 2A, B1 is not equal to 1B, and B2 is not equal to 2B. Therefore A cross B is not equal to B cross A. Now you can always see that for example, if you want a real life time example, you can see codes on vehicles like 3A and A3 are not the same. So always first is first and second is second. So you have to always take, if it is alphabet first, you have to take alphabet first. If it is number first, then you have to take number first. Then in that way only you have to write the code on the vehicles. So now next, what is called as ordered triplet we'll see. Now A cross A is equal to, in brackets we are having A comma B comma C. ABC belongs to A, where ABC is called as the ordered triplet. Now this is called as an ordered pair. You know that AB is called as an ordered pair, isn't it? So now here you are having what is an ordered triplet is when you are having it as A comma B comma C. This is called as an ordered triplet. So now if you are taking example over here, how do we write this ordered triplet? We'll just see one example of this ordered triplet. We have seen what is ordered pair. There we have taken over there. Now we are taking what is ordered triplet. We'll see what is this. So now we are defining a set A is equal to 3, 4. 3 is first, second. These so form the set A cross A cross A. That is ordered triplet. So here that means 3, 4 cross 3, 4 cross 3, 4. So now this is the first set, second set and the third set. So now how do we write this? We'll just see. Now ABC all 3 belongs to A itself. So we are taking first this 3 is from the first set, then you're having 3 from the second and 3 from the third. So the first value is written over here. So you got this. Now next, 3 from first, 3 from second and 4 from the third. So this is coming. Next, 3, 4, 3. Then 3, 4, 4. Then you can write as 4, 3, 3. Then 4, 3, 4. Then 4, 4, 3. Then 4, 4, 4. All 4. So therefore, you are taking the first one from the first set, second from the second set, third from the third set. All are A itself. But here also you have to write in that same order where A, B, C. It is in that order. Ordered triplet it is called. So from first, second and third, all 3 will be written in this order. Next, number of ordered pairs of A cross A is equal to, now you can see here, this is 2, this is 2, this is 2. So it is nothing but, how many ordered pairs did you get? 1, 2, 3, 4, 5, 6, 7, 8. So 2 cubed is equal to 8. So number of ordered pairs of A cross A is equal to 2 cubed, which is equal to 8. Now next, A into infinite set is always equal to an infinite set, because you'll get, this is infinity means even A into any infinity it's the same. So here you'll get again the product, because the second set has infinite number of elements. A cross infinite set will also have an infinite number of sets. Now where A is a non-empty set. Next, A cross 5 is equal to 5 means A into any empty set, you cannot form any ordered pair because the second set is empty. There is no element in that. So there is no means. So therefore A cross 5 is equal to an empty set. Next, n of A cross B is equal to n of A into n of B. That is, number of elements of A cross B is equal to n of A, number of elements of A into number of elements of B. Now we have seen here number of ordered pairs in A cross A, no? So here we are seeing number of elements in A cross B is equal to n of A into n of B. We'll just see what is that example and how is this done. We'll just see here. Now if you consider A is equal to 1, 2, B is equal to 3, 4, number of elements in A cross B is equal to, now you can see what is A cross B. We have got it as 1, 3, 1, 4, 1, 2, 3, 2, 4. So therefore n of number of elements of A cross B is equal to how much? 1, 2, 3, 4 we got. Now what is n of A, number of elements of A? How many are there here? 2 are here in A, and number of elements in B are 2. So therefore 2 into 2 is equal to 4, and you got A cross, number of elements of A cross B is nothing but equal to 4. So therefore n of A cross B is equal to n of A into n of B. Now similarly, if you have A is equal to 1 comma 2, B is equal to 3 comma 4, C is equal to 5 comma 6, number of elements in n of A cross B cross C is equal to what? We'll see. Now here it is A cross B cross C is equal to, we can write it as 1, 3, 5, 1, 3, 6, 2, 3, 5, 2, 3, 6, 1, 4, 5, 1, 4, 6, 2, 4, 5, 2, 4, 6. So all these we can write. Therefore number of elements of A cross B cross C is equal to n of A into n of B into n of C, that is 2 into 2 into 2, which is 8. We have seen that already previously. So I have shown you as an example now, that is 2 cubed is equal to 8. Now we'll go into one more example. In general we'll write down. So if P is equal to ABC and Q is equal to Q, form the sets P cross Q and Q cross P. P cross Q is equal to ABC cross Q. So it is AQ, BQ, CQ. So and Q cross P is equal to Q into ABC, which is equal to QA, QB, QC. So here what are we getting here? P cross Q and Q cross P both are different, but we are just writing down what is P cross Q and what is Q cross P over here. They are not equal, you can see from this. Now next example. Let A be equal to 1, 2, 3, B be equal to 3, 4, C be equal to 4, 5, 6. So here you are having A cross B intersection C, we have to find out, and A cross B intersection A cross C. Intersections and unions we did in the previous chapter. So what is B intersection C? We'll see first here. Now from this you can see what is B intersection C. So if you're taking B and C, what is common in both of them? It is 4. So therefore B intersection C is equal to 4. So therefore A cross B intersection C is equal to, A is how much? 1, 2, 3 cross B intersection C, that is 4. So it is 1, 4, 2, 4 and 3, 4. Next, second what we have to prove? A cross B intersection A cross C, it is what? Now what is A cross B? We'll see. It is 1, 2, 3 into 3, 4. So now we'll write it as 1, 3, 2, 3, 3, 3, then 2, 3, 2, 4, 1, 4, then 3, 4. You can also write it as, if you are writing it in this way, you can write it as 1, 3, 1, 4, then 2, 3, 2, 4, 3, 3, 3, 4. If you write it in this way, it will be more easier. You can write either in this way. I have taken it as 1, 2, 3 for 3 first, then 1, 2, 3 for 4. You can also write as 1 with 3, 4, then 2 with 3, 4, 3 with 3, 4. So it can be written in both the ways. So you'll get the same type of ordered pairs over here. That is first from the first set and second is from the second set. Both are obvious. Then what is A cross C? A cross C is equal to 1, 2, 3 cross 4, 5, 6. So it is 1, 4, 1, 5, 1, 6, 2, 4, 2, 5, 2, 6, and then 3, 4, 3, 5, 3, 6. Now what we are doing is A cross B intersection A cross C will do. So what is A cross B intersection A cross C? What is common in both of them? We'll just round off both of them. Now here there is 1, 4 over here. Here also there is 1, 4. So we are rounding it off. Next we are having 2, 4 over here. Here also you are having 2, 4. Then you are having 3, 4. Here you are having 3, 4. Here also you are having 3, 4. Intersection means which is common in both the sets. So therefore A cross B intersection A cross C is equal to 1, 4, 2, 4, 3, 4 ordered pairs. We have got this. So therefore A cross B intersection C is equal to A cross B intersection A cross C. Now next, if R is a set of all real numbers, there's one more example we'll take. So if R is a set of all real numbers, what is the Cartesian products R cross R and R cross R represent? So here R is equal to A belongs to set of real numbers. Okay. Now R cross R is equal to AB. It consists of all ordered pairs AB, where A comma B belongs to real numbers. Now R cross R is equal to set of all ordered triplets A comma B comma C, where A comma B comma C belongs to R. Next, we'll see, this is a example. This is also one more example which we have. Here the Cartesian product A cross A has 9 elements, among which are found -1, 0 and 0, 1. This is one of your exercise problem. Find the set A and the remaining elements of A cross A. So now here you are having number of elements of A cross A is given as 9 over here. So we have taken it as 9. Now if n of A into n of A is equal to 9, that is 3 into 3 is only going to give you 9. So number of elements in A should be 3, and number of elements in this, it's all obviously going to be 3. So it can be most obviously, because this is one of the ordered pair and this is one of the ordered pair. It is consisting of 3 elements, means one can be -1, the other can be 0, the other one can be 1. So if this is A, then again A cross A only we are taking, no? So therefore we are taking A cross A, means it can be written as -1, 0, 1 cross -1, 0, 1. So you are going to get these ordered pairs. So therefore you can see here very obviously that -1, 0 is one element and 0, 1 is one of the element. So these are the elements which are found in this. So -1, 0 and 0, 1 are the elements. Next, so these are the different types of examples we have seen for Cartesian products. Now we'll just go and see what is relations. What are relations? So we already seen the connection between two objects, isn't it? So what is that? We'll just see. A relation R from a non-empty set B is a subset of the Cartesian product A cross B. So we are using this Cartesian products in relations. It is nothing but a set B. A relation R from a non-empty set B is a subset of the Cartesian product A cross B. The subset is derived by describing a relationship between the first element and the second element of the ordered pairs in A cross B. So there is some relation which is described between these two, A and B. So what is that? We'll just see through examples. Now we have taken here one example, A and B. So what is A cross B? We have to see. A contains of ABC and B contains of 1, 2, 3. Here when we are taking the Cartesian product, we can write directly that A1, A2, A3, then B1, B2, B3. You can see all the blue lines are they're going from first set to second, all the 3 elements of the second set. Then B with the green line, you can see B is going to all the 3 elements of the second set. So in this way you can see is going to all the 3 elements of the second set. So therefore A1, A2, A3, B1, B2, B3, C1, C2, C3. This is the Cartesian product. Now we can create a relationship. Now here you can see that relation R from a non-empty set B is a subset of this Cartesian product. So this Cartesian product, whatever is the A cross B, it is this B is nothing but the subset of this Cartesian product A cross B. So now we can create a relation. Only 1 and 2 shall be present in as the second element. So that means what is the relationship between A and B? We don't want 3 to be in the 3 is there in set B, but we don't want 3 to be used. We want only as a second element as 1 and 2. So this is the relationship which we are going to put between A and B. So this is nothing but it is a subset of set B, isn't it? Set B is containing 1, 2, 3. But whenever we are taking only elements of B, we are going to take as 1 and 2 only we want. So it is subset of set B, isn't it? So here you can see it is nothing but relation R from a non-empty set B is a subset of the Cartesian product A cross B. So from all these Cartesian product A cross B, we'll get one more subset where we don't include 3. 3 won't be in that at all. So this 3 whatever we have written here, all these 3's won't be as the second element in this Cartesian product where we have defined a relation. So therefore A cross B is equal to nothing but in yellow line whatever I have put in there, A1, A2, then B1, B2, C1, C2. Green and red we having. We are not putting anything to 3. So therefore the first element in the ordered pair is called the pre-image of the second element, and the second element in the ordered pair is called the image of the first element. So second element is the image and the first element in the second element is called the image and the first element is called the pre-image of the first element. I'm sorry, second element, and the second element is called the image of the first element. So therefore the set of all first elements of the ordered pairs in a relation R from a set A to a set B is called the domain of the relation. Now here all which elements are there in A are called as the domain, that is A, B, C are called as the domain. Next, you are having the set of all the second elements of the ordered pairs in a relation R from a set A to set B is called the range of the relation. Now what is the relation of here? We are creating one relation. Only 1 and 2 shall be present as the second element. So therefore 1 and 2 are called as the range. 1 and 2 only are called as the range of the set of is called where range of the relation R, and the whole set B, that is 1, 2, 3 is nothing but it is called as the codomain of this. So therefore the whole set B is called the codomain of the relation R, that is range is the subset of the codomain. So now what is this domain, range and codomain? What are its how do we use them? It is nothing but the set of all permissible inputs which satisfy the relation criteria. So you are putting one relation over there. We want only 1 and 2 in the second set, and what are there in A over here? We are having A has all A, B, C. So this is nothing but these are called as inputs. A, B and C are called as inputs, and all these are all called as permissible inputs. And here what are the permissible outputs? 1 and 2 are called as permissible outputs from set B. So therefore those are nothing but the range. So set of all permissible outputs which satisfy the relation criteria. Even domain should satisfy the relation criteria, and even range should satisfy the relation criteria. And what is the codomain? Codomain is all the elements which are there in set B. That is 1, 2, 3 is said to be the codomain, but it need not satisfy the relation criteria. So therefore here which is not satisfying, here what is the domain from there? We can tell that domain is nothing but A comma B comma C, and what is the range from that from this 1, 2, and what is the codomain from that example which we have taken? It is nothing but 1, 2, 3. Okay, so this is the way we can write down what is domain, range and codomain. Now relations representation. So relations can be represented in 3 forms. So roster form, set builder form and arrow diagram, where roster form and set builder form are called as algebraic representation, and an arrow diagram is visual representation. So let A be equal to 1 to 3 so on up to 14. Define a second one. Let A be equal to 1 to 3 so on up to 14. Define a relation R from A to A by R is equal to xy such that 2x minus y is equal to 0, where xy belongs to A. Write down its domain, range and codomain. So now here we have y is equal to 2x. So therefore A is nothing but, from this arrow diagram you can see it is 1, 2, 3, 4 up till 14, and B again A is equal to 1, 2, 3, 4 up till 14. So we can write down what are all the domain, range and codomain. So here domain is nothing but, here you are having 1, 2, 3 up till 14 you are having, but minimum we can take only till 7 because the set A again consists of 14. So therefore 7 into 2 is 14. So still for 7 we can take as the domain. Therefore here you can see what are all the R elements, that is A cross A, A cross the Cartesian product, A cross A is equal to what we'll see over here. So A cross A is equal to 1, 2, 2, 4, 3, 6, 4, 8, 5, 12. That is the relation which is there. It's not A cross A. It is the relation. R is equal to 1, 2, 2, 4, 3, 6, 4, 8, 5, 10, 6, 12, 7, 14. So domain is equal to 1, 2, 3, 4, 5, 6, 7. Range is equal to 2, 4, 6. You can see always the domain is the first element and the range is always the second element, right? So whichever is not underlined, that comes in the range, and the codomain is all those elements in set B. Now, number of relations, how do we calculate this? So here A is equal to 1 to B is equal to 3 means n of A consists of how many elements? 2. So number of elements in set A is equal to 2. Number of elements in set B is equal to 1. So now here you are having number of elements in A cross B is equal to 1, 3, 2, 3. That is 2 into 1, which is equal to 2. So in general we have n of, if n of A is equal to P, n of B is equal to Q, n of A cross B is equal to PQ. So number of subsets is equal to 2 square, which is equal to number of subsets 2 square is equal to 4, which is equal to 5. Then you're getting 1, 3, 2, 3, and the set itself, that is 1, 3 and 2, 3. So this set itself we are taking it as one of the subsets, therefore which is equal to 2 square is equal to 4. Now if n of A is equal to P and n of B is equal to Q, then n of A cross B is equal to PQ. Then the total number of subsets is equal to 2 to the power of P into Q. So if you are taking an example, A cross B is equal to 1, 3, 2, 3, the same thing which we have taken. So you can see empty 1, 3, 2, 3 and 1, 3, 2, 3. So the same thing which I have written over there, it's written here. So that is 2 to the power of 2, which is equal to 4. 4 elements you can see, 4 subsets. These are all sets, not elements. These are all sets which are written in braces, are always sets. Now next, what are functions? A relation is said to be a function if every element of set A has only one image or output in set B. So denoted by f from A to B. So here you are having set A and set B. In set A you are having 1, 2, 3, 4. In set B you have 1, 4, 9, 16. So the image of 1 is 1, image of 2 is 4, image of 3 is 9, image of 4 is 16, and the pre-image of this 1 is 1, pre-image of 4 is 2, pre-image of 9 is 3, pre-image of 16 is 4. So only these are all called as inputs. The elements in a set A are called as inputs. The elements in set B are called as outputs. So now here relation said to be a function if every element of set A has only one image or output. So he is telling only one image, not more than one image should be there from one input or output in set B. So now here you can see from only one input there is only one output is a function. Now if you are having a relation in this way where you are having A to 1, B to 2 and B to 3. So here from 1 to many it's going. So therefore this is not a function. A function, whenever we are defining a function, we always have a one-to-one relationship. So therefore here always whenever it is from 1 to many, it is not a function. So therefore 1 to many is not a function. Many to 1 can be a function. Now we are having a Venn diagram in this way where you are taking this as set A, this as set B. If you are taking arrow diagram, I'm sorry, not Venn diagram, it's an arrow diagram. You are taking A, B, C, and this is 1, 2, 3. This can have 1, this can be in this way, A1, B1, C1. It can be in this way. This is said to be a function, but B can be repeated. The elements in set B can be repeated, but the elements in A, set A cannot be repeated. So therefore many to 1 is also a function, 1 to 1 is also a function, many to many is not a function, and whatever I have written as cross over here, 1 to many is also not a function. So if it is a tick mark, it is a function. No, it is not a tick mark, it is not a function. Now we'll go into examples and see which is a function, which is not a function. Now we are having here given what is P and what is Q. P is equal to 2, 1, 3, 1, 4, 2. So you can see here all the first elements and nothing is repeated. All are different, 2, 3, 4. So therefore this can be a function. So here you can see here in this diagram AB, you are having 2 3 4. This is going from many, all of these 2 3 they are many, and this is going to 1 itself over here. So many to 1 is a function, or 1 to 1 is also a function. But in the second one you can see the first element is repeated here, 2 2 is repeated. So therefore this is not a function. Therefore the inputs have to not be repeated. The outputs can be repeated how many ever times we want, but the input should not be repeated. If it is repeated, it is not a function. Therefore here this is 1 is going to many. See here, it's going to 2 and 4. 2 is going to 2 and 4. Therefore it is not a function. It should always be either 1 to 1 or many to 1. Now next we'll see what is a real and real valued function. In this you have permissible inputs are nothing but domain, permissible outputs are range. So both are real numbers or subset of real numbers. And if it is a real valued function, then you have range is always real and domain need not be real. So whenever we are taking examples of real functions or real valued functions, so in this range is always real. Domain need not be real in the case of real valued functions. But in the case of real functions, permissible inputs also should be real, and even or subsets of real numbers. Permissible outputs will always be subsets or real numbers. Next we'll go into what are the different types of graphs we can take. Graph of identity function is in this way. So therefore you can see what are the x values and what are the y values for this. So if x is 1, y is also 1. If x is 2, y is also equal to 2. If x is 3, y is also equal to 3. So on. So now here you have what is the domain and range of this identity function. Domain is set of all real numbers. Therefore the range also is over here. Range is also set of all real numbers. And the graph is a straight line. It passes through the origin, and this is the way we write f of x is equal to x is called as, such a function is called as an identity function which is passing through the origin. Next graph, what is a constant function, we'll see. Now this is called as the constant function. Over here k is a constant, that is f of x is equal to k, that is y is equal to some value. It is parallel to the x axis over here. So here you can take this y is equal to 3. This is a constant where k is equal to 3 over here, and it is parallel to the x axis. So here you are having always the domain as all real numbers, but the range is only 3. So it is fixed. So here you are having x and y. So if x is 1, y is 3. If x is minus 1, y is 3. If x is 0, also it is 3. Therefore here you are having 2, 3. So whichever number, therefore here you are having what is the domain. Domain is nothing but it is equal to set of all real numbers. X belongs to real numbers and range is k. You can take it as k, or in this case it is 3 over here. This is called a constant function. Next, what is the graph of a rational function? Over here you are having a rational function, what f of x by g of x, where f of x and g of x are polynomial function and g of x is not equal to 0. Example, f of x is equal to 1 by x. Is equal to 1 by x. X cannot be equal to 0, isn't it? Or it is written as f of x by g of x, where g of x, f of x and g of x are polynomial function and g of x is not equal to 0. So over here you have except 0. X can take all the values, but x is not equal to 0. And its range is also all real numbers except 0. So range is also, domain is all real numbers except 0. It is not taking 0. Range is also the same thing. It is all real numbers except 0. It is not going. Now graph of a modulus function. Modulus means that whenever if it is in negative sign, it becomes a positive one. So therefore here you will have f of x is equal to, for modulus function you can have it in this way. It is always equal to x greater than or equal to 0, minus x is less than 0. So now here what is domain, what is the range? So here you are having f of x is equal to mod of x, means that is y, it is equal to y. So if x will take what kind of values? The domain will be all, domain can take all real values. X belongs to set of all real numbers, that is -1, 1, 2, -2, 0, anything you can take. So 3, -3 and so on. It's all real numbers. But here always whenever we are taking this y, it is always positive value. It will be always positive values. So now we have what is called as graphs of signum function. Signum function is a function such that f is defined from real numbers to real numbers itself. That is, you can see over here, if it takes 1, if x is greater than 0, it is y is always equal to 1 if it is greater than 0, and it is taking, y will take value 0 if it is x is equal to 0, and takes -1 if x is less than 0. So here we can see this is the way it is defined. So this is a different type of graph which you are having. So here domain of the signum function is R, and the range, so domain is what over here? Domain is set of all real numbers, and the range is what over here? The range is equal to set of all -1, 0 and 1. It takes only these numbers. When it's x greater than 0, x is equal to 0 and x is less than 0. These three numbers it takes. So this is the range and domain of the function. Next, we'll just see what is this example. Show that f is a function. You're given that f of x is equal to x square. X lies between 0 and 3. And here f of x is equal to 3x if x lies between 3 and 10. And here you have g of x is equal to x square if x lies between 0 and 2, and x it's equal to 3x if x lies between 2 and 10. So we'll just see for the first function. For f of x we'll define how to do this. So we'll just do what is x and y over here. So what are the values which x can take and what are the values which y can take over here? So it is taking from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So when x is from lying between 0 and 3, it is nothing but x square. So this will become 0, this will be 1, this will be 4, and this will be 9. Now from x lying between 3 and 10, that means it's again 9. 3x means 3 into 3 is 9. Then 4 3s are 12. 5 3s are 15. 6 3s are 18. 7 3s are 21. 8 3s are 24. 9 3s are 27. 10s are 30. So this is the value of y when x is between, from here from 3 to 10 it is 3x, and from here to here it is x square. So therefore you are getting these values over here. Next, now this is a function or not, because 3x square, for 3 it is also 9, for 3x it is also 9. So therefore there is a 1-to-1 correspondence for this. So therefore this is a function. Now we can tell that f of x is a function. We'll see what is g of x now. For g of x we are having x values and y values. What are they? We'll just see. So for this you can take it as 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. Now for 0 to 2, it is x square. So here you are getting 0, 1 and 4. From this part it is again 3x. Means 2 3s are, you are getting here 6, 3 3s are 9, 4 3s are 12, then 3. So in the same way as whatever values are there that side, we can just write down those values. But this is not a function because 2 is taking two values over here. You're getting 2 to 4 and 2 to 6. So therefore this is not a function. So always one to many cannot happen. It is always one to one correspondence which we can take for. So algebra of functions, addition of two real functions f from x to r and g from x to r are two real functions where x belongs to r. Then f plus g from x to r is defined as f plus g of x is equal to f of x plus g of x for all x belongs to r. Subtraction of two real numbers. F is a function from x to r, g is a function from x to r, are any two real numbers where x belongs to r. We define f minus g of x, that is from x to r, by the definition f minus g into x is equal to f of x minus g of x for all x belongs to capital X. What is multiplication by a scalar? F from x to r is a real function and alpha be a scalar. Then the product alpha into f is a function from x to r defined by alpha into f of x is equal to alpha into f of x where x belongs to capital X. Now the next one we have multiplication of two real numbers. So how do we do this multiplication of two real numbers? F from x to r, g from x to r be two functions such that f into g is also a function from x to r defined by f into g of x is equal to f of x into g of x for all x belongs to r. Next we have quotient of two real numbers, also is defined in the same way. F from x to r and g from x to r be two real functions where x belongs to r. Then the quotient is denoted by in the following manner, that is f by g of x is equal to f of x by g of x. So now here if we take examples, we'll see how we can write this. If we define one of the f of x and what is g of x, how can we add both of them? We'll just see. Take f of x is equal to x square, g of x is equal to 2x plus 1. So f plus g of x is equal to f of x plus g of x means it is equal to x square plus 2x plus 1. So same example if we take for subtraction again, we'll see what we get. We can write it as f minus g of x is equal to x square minus of 2x minus 1. We can write it in the same manner if we are taking the same values. Function alpha is equal to 2, f of x is equal to x square. We can write it as alpha into f of x is equal to 2 into f of x, which is equal to 2 into x square. Next, multiplication of two real numbers also we can do in the same way. We have f of x is equal to x square, g of x is equal to x plus 1. Then f into g of x can be written as f of x into g of x. So which is equal to x square into x plus 1, which is equal to x cube plus x square. Next, quotient of two real numbers. The same way we can take some example for this also. So for this also we are taking one example. F of x is equal to x square and g of x is equal to 2x plus 1. So how do we write this? F by g of x is can be written as f of x by g of x, which is equal to x square by 2x plus 1. So in this way we can write down the addition, subtraction, scalar multiplication, then quotient.